All right, welcome back. Today we're talking about energy. So, our goals for today's lesson are first to identify the major types of energy in the physical world. Second, we want to be able to explain the role of electromagnetic radiation in the Earth system. And then we want to evaluate some of the sources of energy used by human societies. So, what is energy? We're going to start with the perspective of a physicist. So, from a physics point of view, energy is defined as the ability to do work. And work is defined as the displacement of something by the application of force. So, a way you can think of this is if you remember Newton's first law, that an object will tend to either remain at rest or in motion at a constant speed in a straight line, unless it's acted on by some outside force. So we have that default behavior of everything that they're going to stay at rest or moving in a straight line at a constant speed. And if you change that, if something alters that default state, it's because you're using energy to do work on it. So on the picture there, that ball is default state is to sit there on the table, and that cat is going to use some energy to do a little bit of work to that ball to knock it off of there. So there's a number of different units that we might use when we're measuring energy. And my goal with this slide is just for you to be familiar with these units so that you recognize them and so that you know, oh, we're talking about energy. You don't have to know the exact conversion factors and so forth. If you ever need to know, how many calories is one BTU or something, you can look it up. There are lots of calculators online that can do that for you pretty easily. But I want you to sort of have a conceptual understanding of what these units are and why we might talk about one unit or another. So the basic unit of energy in the SI or metric system is the joule, represented by a capital J. So that's our basic unit used in most scientific applications. And a joule is defined as the energy used when a 1 Newton force moves an object 1 meter. So that's the definition, but that definition probably doesn't mean a whole lot to you because you can't picture what that means. So here's an example. I have this tube of Benadryl that happens to be the first thing that I found in my house. It is 3.5 ounces plus a little more for the packaging. And so that means that if I take this object and I raise it up 1 meter, so I'm moving it 1 meter against the force of gravity, and it weighs 3.6-ish ounces, which is equivalent to 1 Newton, I am doing 1 joule's worth of energy. I'm using 1 joule of energy to lift this little tube of Benadryl up 1 meter. So hopefully that gives you a sense of the amount of energy that a joule is. It's not a huge amount of energy. We're usually dealing with a whole lot of joules, and sometimes we'll use things like megajoules, where we have a larger unit made out of a whole lot of joules. But that's about what that amount of energy is. Another unit of energy that you may run into a lot, especially when we're talking about powering our homes and our cars and everything, might be a kilowatt hour. So a kilowatt hour is defined as the energy delivered by 1 kilowatt for 1 hour, as the name suggests, and that ends up being equivalent to 3.6 megajoules. So when you have mega in front of a scientific unit, that means a million. So 1 kilowatt hour is equivalent to 3.6 million joules. So if you're looking at your electricity bill and it tells you how many kilowatt hours of electricity you used last month, you could convert that to joules by just multiplying by 3.6 million. Another unit that we run into is a BTU, or British Thermal Unit. And this one is usually used in heating context. So if you are like looking at furnaces or something, you might find them described in terms of how many BTUs they can put out. And a BTU is defined as the energy needed to heat 1 pound of water by 1 degree Fahrenheit. So this is very much not a metric unit here, but that ends up being equivalent to about 1,055 joules. So again, if you needed to convert, you could just multiply there. BTUs, as I said, are mostly found in, you use that unit in a lot of heating related applications. And then A fourth unit used to measure energy that you may run into is the calorie. And calories are particularly confusing because the word is used differently in the United States than in other parts of the world. So the basic definition of a calorie is that it's the amount of energy needed to heat 1 milliliter of water by 1 degree Celsius. So the amount of energy you need to put into 1 milliliter of water to heat it up by 1 degree Celsius, that is a calorie. We most often see calories used to describe food, right? You look at the packages of food you buy, and it tells you how many calories are in that food. But an actual calorie is a very tiny amount of energy. So the numbers on the food packaging are actually in kilocalories. So kilo is a prefix meaning 1,000. So they're actually talking in groups of 1,000 calories when you see how many calories are in your candy bar or whatever. And if you look at food packaging from other countries, you'll often see it listed as kilocalories or KCAL. They'll have the kilo on there. For whatever reason, in the United States, we decided to abbreviate kilocalorie as calorie. So the things that are labeled calories in the United States are actually the same as kilocalories overseas, and they would be then equivalent to the energy needed to heat 1 liter of water by 1 degree Celsius. If it takes 1 regular calorie to heat a milliliter of water 1 degree, then you've got 1,000 milliliters is a liter, so that would take 1,000 kilocalories or 1 American calorie. So because of that confusion, it's not a great unit to use for a lot of applications, but I wanted to mention it because you see this unit all over the place. It's a popular one to run into in your everyday life. But all of these are just units that we can use to measure energy, and you can convert them into each other if you know what to multiply by. But again, for the purposes of this class, I'm not going to make you do a lot of that math right now. I just wanted you to be familiar with the energy units that might crop up from time to time. So let's talk about the different types of energy that we have in our world. We can divide the types of energy into two main categories. We have kinetic energy, which is the energy involved in motion, things moving, and we have potential energy. That's the energy involved in the position of things. And we can illustrate all of these by looking at this example of some people on a roller coaster. These people are being affected by a whole bunch of different kinds of energy in the course of their ride. So we'll start with breaking down different kinds of kinetic energy. We have 4 kind of subtypes of kinetic energy. The first is mechanical energy. This is the energy of the motion of macroscopic objects. So macroscopic means basically big enough for us to see. We don't need a microscope to see it. Stuff that we can see move around, that is mechanical energy. So when that roller coaster car goes down the track, that is mechanical energy that is moving that roller coaster down the track. Another type of kinetic energy is thermal energy. Thermal energy is the motion of the atoms within an object. So all of the atoms in the roller coaster car, in the track, in the people, in the air around them, all of those atoms are wiggling around. They are moving, bopping back and forth. And that is thermal energy. And we're going to talk a lot more about thermal energy in just a little bit. But for now, just remember it's the energy involved in the movement of atoms in any object as they wiggle and bounce around. We also have electrical energy. So electrical energy is carried by the motion of charged particles. So if you plug something into the wall and electrons are moving through your wires to turn your light on or whatever, you're using electrical energy. And so that roller coaster may have an electrical motor that drags the car up to the top of the next hill on the track. It's using electrical energy there. And then we have electromagnetic energy. So electromagnetic energy is energy carried in electromagnetic waves. And so this is, again, one we're going to spend more time talking about in a little bit, but this is a category that includes things such as microwaves, X-rays, visible light, gamma rays, radio waves. There are lots of different types of waves that carry energy, and those are grouped under electromagnetic energy. So those are some types of kinetic energy, energy where things are moving. Then we have our potential energy, energy that is involved in the position of things relative to each other. So we can break that down into some subcategories as well. So one of those is elastic potential energy. That is the energy that's stored in something that's held under tension. So if you imagine if you have a spring and you've squished it and you're holding it squished, that spring now has potential elastic energy. And you'll see that converted into kinetic energy if you let the spring go and it returns to its previous size. Or on the other hand, if you take a rubber band and you stretch it out, you're holding it under tension, you've got elastic potential energy in that rubber band, and if you let go, it will snap back together, turning that potential energy into kinetic energy as the rubber band moves. Another form of potential energy is chemical potential energy. That's energy that's stored in the bonds between atoms. So chemistry is all about how we arrange atoms to make different kinds of substances. And so when you form certain substances, it consumes energy, and that energy is then stored as potential energy in the bonds between those atoms. And then if those bonds were to break, that energy would be released and could transform into another form. Then we have nuclear potential energy, which is a similar idea, except now we're talking about the bonds that hold atoms together in themselves. So rather than sticking two atoms together that holds all the parts of the atom together, we're dealing with nuclear potential energy. And then we have gravitational potential energy. When we have two objects that are separated in space, but gravity is pulling them together, we have potential energy there. And since the Earth dominates our perceptions of gravity, right? The Earth has so much more gravitational attraction for everything on it than any of the things on it have to each other. We can think of gravitational potential energy as essentially contained in something's elevation. The farther you are away from the center of the Earth, which is what gravity is trying to pull you towards, the more potential energy you have, more gravitational potential energy you have. So when that roller coaster car was at the top of the track, it had a lot of gravitational potential energy because it was farther from the center of the Earth, and then that energy gets converted into kinetic energy as it slides down the track. And all of this energy can neither be created nor destroyed. So the law of conservation of energy, you can't make or destroy energy. All you can do is convert it from one form to another. So I just mentioned, if you have the gravitational potential energy of that roller coaster at the top of the track, that can get converted to kinetic energy when the roller coaster slides down the track. Then you may apply some electrical energy to drag it back up to the top, where it now has that electrical energy has now been converted back into gravitational potential energy because it's sitting at the top waiting to slide down again. So we can convert energy between different forms. We can move energy from one place to another, but we can't create or destroy it. And we can add up the total energy present in some system. If we have a collection of interacting parts, so if we look at that roller coaster, we've got the cars, their wheels, the track, the people in them. That's a collection of interacting parts. That is a system. And we could add up the total energy present in that system. If that system is an open system, that means it can gain or lose total interaction through gain or lose energy through interaction with its environment. So when the motor drags the roller coaster cars up to the top of the track, we're adding new energy into the system. Right? We're bringing new energy in from the electrical grid and from the power plant that made it, et cetera. So we're adding new energy into the system. So it can gain energy, it can also lose energy. So for example, as the car slides down the track, there's going to be friction with the track. That's going to create thermal energy. Right? It's going to heat things up, but then that thermal energy is going to get radiated out away from the roller coaster, and it's going to leave the system. So energy can come in and go out of an open system. A closed system would be a system that has no interaction with anything outside of it. And in that case, its total energy has to stay the same. It can move around, it can get converted into different forms within the system, but it can't increase or decrease the total energy in that system if it is closed, if it has no interactions with anything outside of it. So then that leads to the question, is the Earth an open or a closed system? Is the Earth an open or closed system? Well, the Earth is an open system because we are constantly receiving energy from the sun. So if the Earth is our system, sun is outside, but we interact with the sun. We're constantly receiving energy from the sun. We're also constantly losing energy into space. So the total energy of the Earth could go up or down depending on the balance of these different kinds of factors because we are an open system. So that energy can't be created or destroyed, but it might leave our system or it might come into our system from outside. So let's drill down now to thermal energy. So if you remember, thermal energy was one of our kinds of kinetic energy. It's energy of movement, and it's specifically the movement of the particles, like atoms and molecules that make up an object. They are moving around, jiggling and wiggling, and all of the energy involved in that motion is thermal energy. So we could add up the total thermal energy of an object if we add up all of that energy from all of that motion of atoms. And if we know our thermal energy, we can also know our temperature, which is the average thermal energy. So the average kinetic energy of all the particles in an object is the temperature. So temperature is an average thermal energy. We're talking about the total amount. So a warmer thing is a thing that has more motion going on in its particles. You can see that in the little diagram there. The hot water, those particles are moving around a lot. The cold water, they're moving around less. So the hotter something is, the more its atoms are wiggling and jiggling around through kinetic energy. So that means then that we have a theoretical lowest possible temperature. So if hot things have more motion in their atoms, cold things have less motion in their atoms, eventually you could get something so cold that the atoms are not moving at all. If there is zero kinetic energy in those atoms, they are not moving around relative to each other at all. That's the lowest possible temperature. You can't get colder than that. You can't have less than zero motion in your atoms. So we call that absolute zero. Lowest possible temperature, no particle motion happening. And that happens at about negative 273 degrees Celsius or negative 459 degrees Fahrenheit. So that is extremely cold, not something you're ever going to experience in your life, but that is the theoretical lower limit to how cold something can get. On the other hand, there is no theoretical limit to how hot something can get. The atoms can always be moving around more. There's always a possibility for more motion in those atoms. Now, things start to get weird when stuff gets really, really hot. Substances start to behave in strange ways that are unfamiliar to us here in living our everyday lives on Earth, but there's no theoretical limit. There's no cap to how hot something could possibly be. And so the diagram here just gives you a comparison of the Celsius and Fahrenheit scales, because Fahrenheit is probably more familiar to most of you. It's the usual way we measure temperature in the United States when we're talking about the weather outside or your body temperature or cooking or stuff like that. But in a science course, we're going to use the Celsius scale. So you need to remember to convert between those if you've got a mix of different temperature scales. And there's an equation that you can use that will give you the exact number. Your temperature in Fahrenheit is equal to your temperature in Celsius times 9/5 plus 32. So that's accounting for the fact that a Fahrenheit degree and a Celsius degree are different sizes, and accounting for the fact that they have different baselines, right? 0 degrees Celsius, which is the freezing point of water, is equivalent to 32 degrees Fahrenheit. So they don't have the same baseline, so you have to adjust for that as well. There are plenty of online calculators that can do that for you if you need to get an exact amount, so I'm not going to spend time having you practice converting between Fahrenheit and Celsius. But I would ask you to keep in mind a rule of thumb that 1 degree Celsius is very roughly about 2 degrees Fahrenheit. Right? It's actually 9/5 Fahrenheit degrees, but that's very close to 10/5, which would be 2. And so this is a useful rule of thumb when we talk about temperatures, and especially when we're talking in terms of climate change, and we're talking about 1 or 2 degrees Celsius changes that can sometimes seem like hardly anything because you're used to thinking in Fahrenheit, where degrees are half as big as they are in Celsius. So when you hear about temperature changes that are given in Celsius, then just kind of mentally multiply by 2 to get in the ballpark for how much temperature change we're talking about in Fahrenheit degrees, if you're more familiar and more comfortable thinking in Fahrenheit terms. So let's dig into thermal energy some more and look at how it moves around. So thermal energy wants to move around. It wants to get into anything else around it. And there are 3 main ways that thermal energy can be transferred from one place to another, from one object to another. So one is conduction. So energy will pass from one object that has more energy, higher temperature, into another that is touching it, that has lower energy, lower temperature. So we can see this illustrated with the example of the pot on the stove. So the pot has heated up from being on the stove, and because the bowl of the pot touches the handle, some of that energy is being transferred through conduction into the handle. The handle is warming up because it touches the pot, and so that high amount of thermal energy that's present within the pot is making its way into the handle through conduction. Another way thermal energy moves around is through convection. So convection is the movement of a fluid that carries its energy along with it. So by fluid, we mean both gases and liquids. So gases and liquids are both fluids because they both move around. And so when fluids move, they carry their thermal energy with them. So what you've got going on in that pot, it's being heated from the bottom. So the water at the bottom of the pot gets hot first, and then it starts to rise in the pot because warm things tend to rise. So the hot water from the bottom of the pot will start to rise up. It will be replaced by cold water coming down from the top. And now that cold water has come down to the bottom, and it's going to get heated up by the stove, and it's going to rise. So that water is circulating within the pot. You've got these currents moving that water around in the pot, and those currents will spread out and mix that thermal energy through the pot. So if you have a pot of water, it will heat more evenly through than if you had, say, a solid object. And you may have encountered that if you had, say, a piece of frozen food, like say a frozen, block of hamburger that you were trying to heat up. You put it in the pot. The bottom of it might totally thaw out and start cooking while the top is still frozen because it's solid. So there's no convection, nothing moving the heat up through your frozen block there besides just conduction. Whereas if you had something that was in a pot of water, it would heat more evenly through because you've got that convection mixing the water and moving the heat from the hot places to the cold places as that fluid moves. So we've got conduction, we've got convection, and then we've got radiation. Anything that has a temperature above absolute zero, so anything that has any motion in its atoms at all, is going to produce electromagnetic radiation. That thermal energy is going to convert to electromagnetic radiation and get radiated out from that object. So as you're standing next to your pot on the stove, you can feel it. You can feel the heat coming off of it because there is electromagnetic radiation being produced by all the hot objects there, by the burner, by the pot, by the water in the pot, and it is radiating out and hitting you, and then your body is absorbing it. And so you are feeling that heat even without touching the pot or touching the water in the pot. So these are three ways that thermal energy moves from one object to another. So next, I want to talk about that electromagnetic radiation. But to do that, first we have to understand waves, because electromagnetic radiation moves in the form of waves. So in general terms, a wave is an oscillating displacement in some medium. You've got some stuff, and it is wiggling back and forth in a predictable, consistent kind of way. So you've got this oscillation in some sort of medium. And when that happens, that can transport energy. So the wave will wiggle back and forth, but energy moves along that wave. And when we have a wave, we can measure that wave in several different ways. We have some different measurements we can make of the wave. So we have the wave length, which is represented by the Greek letter lambda there. And the wavelength is the distance between two corresponding parts of the wave. So that wave will make a repeating pattern. And so if you find two of the same spot in that pattern, such as two of the crests there, which is what's shown in the diagram there, they're measuring from the top of one wave to the top of the next. So you're measuring between two corresponding parts. That distance is the wavelength. You also have the frequency, which is the number of waves that pass a particular spot in a unit of time. So as that wave is moving, certain number of those waves will go past a given spot in a certain amount of time. That is your frequency, how frequently you see the same part of the wave go by. And you also have the amplitude. So that is the height of the wave. So we measure that from the midpoint of the wave. And so the height of the crest or the depth of the trough is the amplitude. So is the wave making really big deviations from that midpoint, or is it making very small deviations from the midpoint? That is the amplitude of your wave. So we can measure wavelength, frequency, and amplitude to describe a wave. How is it moving? Then we can divide our waves into two basic types based on the medium that they travel through. So waves involve an oscillation in some medium. So depending on the medium, we might have two different kinds of waves. So one type of wave is a mechanical wave. A mechanical wave is moving through a medium made out of matter. So we have stuff, and that stuff is wiggling around. That is a mechanical wave. And so some examples of mechanical waves are things like ocean waves. So the medium there specifically is the ocean water, and so the waves in the ocean, the water goes up and down, and energy is transported across through those ocean waves. We have seismic waves. So that's the waves that are produced by an earthquake. The earthquake shakes the ground, and that shaking is a wave, and it spreads out through the earth. So the earth there is your medium carrying your waves away from the epicenter of the earthquake. Or sound waves are a form of mechanical waves. When I'm talking to you, I am using my vocal cords to vibrate the air coming out of my mouth, and those air vibrations are a wave that travels through the air to your ears if you were sitting here with me, or to my microphone, where they're converted into electrical signals, which go to your speakers, which then are converted into mechanical waves in the air going to your ears. So mechanical waves are waves that are carried through a medium made out of matter. Then we also have electromagnetic waves. These are waves that involve movement in the electromagnetic field. So the electromagnetic field sort of surrounds us all the time, and it can carry waves through a vacuum, through a space where there is no air or any other matter that could carry a mechanical wave. And I've put this picture of a space battle from Star Wars up here to illustrate the difference between mechanical and electromagnetic waves. So as these spaceships are having their battle in Star Wars, they're going to create a whole bunch of waves because lots of energy is being used, and it's going to be traveling around. And when you're watching this on the screen, you are both seeing and hearing this space battle. Right? You are watching the spaceships fly around, you're watching their lasers hit each other and blow each other up, and then you're also hearing it. So if you're a Star Wars fan, you can probably imagine they have very distinctive sound engineering and meow, pew pew pew, all of those kind of noises. Right? Go watch some Star Wars if my imitations of it aren't good enough. But the thing about the Star Wars movies is that if you were in a real space battle of that type, you would see everything, but you wouldn't hear anything. It would be silent because sound waves are mechanical waves. They require matter to travel through. So we're used to being able to hear some sort of a battle like this happening because we're used to those happening within our atmosphere. So if we had, modern day armies shooting at each other, we could hear their vehicles driving around. We could hear their gunfire. We could hear the zoom of the planes going overhead because they're all moving through the air, and the air carries those sound waves to us. So we're used to being able to hear what happens in a battle like this. But if we were in space, space is a vacuum. There's no matter. Nothing could carry those sound waves. So those spaceships blowing up, that would be entirely silent, except to the pilot inside, right, who has their own little air bubble that they could hear what's happening to their own ship, but you couldn't hear what's happening to anybody else's ship. So it would be completely silent in reality, but you'd still be able to see it because seeing involves electromagnetic waves. Light is a form of electromagnetic radiation that can travel through a vacuum. So if you were at this space battle in real life, you could see everything. You could see the laser fire, see the ships flying around, but they would be silent. But that would make for a boring movie experience. It wouldn't be as immersive, and so the fine folks at Lucasfilm put those inaccurate sounds into their movies to make us have more fun there. But the fact that you couldn't actually hear a space battle if you were actually in space, I think illustrates the difference between mechanical waves that have to travel through matter as a medium and electromagnetic waves that travel through the electromagnetic field, which means that they can cross a vacuum. And when these electromagnetic waves move through this vacuum, they're moving at the speed of light. And I put speed of light in quotes because this really isn't just the speed of light. This is the speed of all electromagnetic radiation. This is the speed of light and the speed of radio waves and the speed of X-rays and the speed of microwaves. All of these types of electromagnetic radiation are moving at that same speed. And since we have that constant speed, it's the same speed for all these types of radiation, that means our wavelength and frequency are going to be the inverse of each other. So as long as the speed is held constant, then a lower frequency means a higher wavelength. If fewer waves go by in a given amount of time, that means those waves must be very long. So you've got a long wavelength. If a lot of waves can go by in a specific amount of time, then you've got a high frequency but lower wavelength. These are lots of little waves going by versus a few larger waves. So frequency and wavelength are inverse of each other when we're talking about electromagnetic waves, where the speed is always the same. Mechanical waves travel at a variety of different speeds, and so that inverse relationship may not hold. Another important thing to keep in mind is that I said waves carry energy. Higher frequency waves carry more energy. So there's more energy in a high frequency wave than in a low frequency wave. So a high frequency, that means, again, low wavelength is going to have more energy to it. Now, the speed of light is the speed in a vacuum. If there is no matter getting in the way, this is how fast electromagnetic waves move. But when they pass through matter, then they can be absorbed, bent, slowed down as they go. And so that means that light isn't necessarily moving at exactly the speed of light all the time if it's not coming through a vacuum, and likewise with these other types of radiation. And that is the principle behind things like the bent straw illusion. So that picture, probably something that you've seen when you stick something into water. It looks like it's bent or broken at the surface of the water. That's because the light reflecting off of it and bouncing back to your eyes for you to see it is getting bent and slowed differently going through the water than through the air. And since you have these two very different media right next to each other at the surface of the water, you can see that difference really clearly. So I've been mentioning some types of electromagnetic radiation, so I want to give you the full chart. So these are the different types of electromagnetic radiation that we have in our universe. So these are the different types of radiation that are going to fall into this category and are going to work like electromagnetic radiation. So this spectrum, if we start with the very long wavelength and therefore low frequency waves, we have things like radio waves. Then we move up to microwaves, then to infrared. So infra means below, so this is below red. Then we get into our visible light. So visible light is just another type of electromagnetic radiation. It happens to be the type that our eyes have evolved to be able to detect. And different colors of visible light have different wavelengths. So you can see that the longest wavelength, so the lowest frequency type of visible light is red. Then as you move up, it goes to yellow, to green, to blue, to violet, as you're getting smaller and smaller wavelengths, higher and higher frequency, and higher amount of energy that's being carried. So all of our visible light, our different colors, are based on their different wavelengths, and you can match up an exact color to an exact wavelength of light that produces that color when your eyes absorb it. So we go from infrared through the different types of visible light, from red to yellow to green to blue to violet, and then we get to ultraviolet. So ultra meaning beyond, right? So our ultraviolet radiation is now even smaller wavelengths and even higher frequency than the visible light. And then we move up to X-rays, and eventually to gamma rays. So we have these different wavelengths, different frequencies, and different amounts of energy that they're able to carry. And you might kind of be able to see that by just thinking about the effects of these different kind of radiation hitting you. Because the more energy radiation has, the more stuff it can do to you, the more effect it can have on you. So if we look at radio waves, those are our lowest frequency, longest wavelength form of electromagnetic radiation. You've got radio waves passing through you all the time. There are natural sources of radio waves as well as lots of artificial ones, broadcasting music and everything. And they can just pass right through. They do zero damage to you. They have zero effect on you because it carries so little energy. You get up into things like visible light. Visible light can have significant effects on things that it hits. It can, cause impacts on your skin, and then you get up to ultraviolet, which becomes the radiation that we get really worried about with things like skin cancer, right? That's why it's ultraviolet, not infrared radiation that you need to block out with your sunscreen, because it's shorter wavelength, higher frequency, higher amount of energy that it's carried, so that ultraviolet radiation is able to do more damage to your skin than visible light would do. And then, of course, X-rays are even more powerful. That's why they can see inside of you, and why you have to be very careful not to get excess X-rays. So you go to the dentist to get an X-ray on your teeth, and they put the lead shield over you, and the person operating it steps out of the room, and people that operate X-rays regularly have a little badge that absorbs the X-rays and shows how much radiation they've gotten so that they don't get too much, and that could cause problems for their health. And then gamma rays being the most powerful of our types of electromagnetic radiation. So that's the spectrum of different kinds of things that are part of our electromagnetic radiation. So we call them by different names to describe some of the different effects that they end up having, but they're really just different wavelengths and different frequencies of the same stuff. Right? A radio wave is just visible light stretched out and slowed down in essence. So now I want to change gears a little bit and talk about energy from an earth science point of view. So we've gotten kind of the physics perspective on energy. Now I want to talk about how energy gets discussed among Earth scientists, where often when we're talking about energy, we're specifically interested in sources of energy that are used to do the work that's important for the functioning of human societies. So there are certain things that we as people need to use energy for, and we have to worry about where are we going to get that energy from. And that's often the specific area of energy that Earth scientists are interested in. What are the sources of those kinds of energy? What are the impacts on the world of using them, etc.? Because we've got a lot of people in the world driving a lot of cars, turning a lot of lights on, and all that stuff needs a lot of energy. So for the remainder of this lesson, we're going to just take a brief look at some of these types of energy that are commonly used, some of the ones that might be producing the energy that you are using today, and just talk a little bit about where they come from and fit them into this framework of what energy is from a physics point of view. So let's start with the most basic, most important for the history of human civilization energy source, which is muscle power. So this has been the main source of energy for most people for most of history, and it continues to be important. You still do lots of things using the power of your muscles or depend on other people to do things with their muscles. This also encompasses domestic animals whose muscle power we might take advantage of, like the horse-drawn reaping machine that is in the picture there. And so essentially what we've got here is we start with solar radiation. So the sun is up there. We've got nuclear fusion going on in the sun. That nuclear energy is released and turns into electromagnetic radiation that gets beamed down to the Earth. When it hits the Earth, plants take that electromagnetic radiation and convert it into chemical potential energy through photosynthesis. So that solar energy is getting stored in the compounds that the plant is manufacturing during photosynthesis. Then an animal, whether that's a human or a horse or whatever, will eat that plant. We will release that chemical potential energy by digesting the food, and we'll convert that energy then into mechanical energy by doing something, by picking stuff up, walking around, dragging things, cutting things, whatever work that we're doing. So you can see this chain of conversion of different types of energy. We have nuclear energy turning into electromagnetic radiation, turning into chemical potential energy, turning into mechanical energy. And the importance of muscle power as an energy source is reflected in the fact that we still talk about the power of different kinds of engines in terms of horsepower, which is a unit of work based on how much work a draft horse could do. So we still analogize things to the muscle power of animals because that was so important for human societies for so long and continues to be so important in so many ways. Another very historically important source of energy for human societies is biomass. So here, we start out the same. We've got the sun, has its nuclear reactions, sends electromagnetic rays down to Earth that gets absorbed by plants, converted into chemical energy through photosynthesis. But then in the case of biomass, instead of an animal eating that plant, we burn it. So using fire, we can release that chemical potential energy, turn it into thermal energy, which we can then do stuff with. So we might just directly use it for heat. So we're using biomass energy anytime you put wood in a fireplace to heat your house or cook over a wood fire, which is how people got warmth and cooking for most of human history. We can also put biomass into some sort of an engine to get other types of energy out of it. So the photo there shows a gas pump where you can get ethanol. And probably many of you have seen gas pumps advertising or letting you know that certain blends of gas contain certain percentages of ethanol. Ethanol is a biomass energy source that comes originally from a plant in the United States that's usually corn. And so that chemical potential energy that was stored up by that corn as it grew goes into the fuel. You put it in your car's engine burns it and converts that into the mechanical energy that drives your car. You could also burn biomass energy in a turbine where the thermal energy heats up water into steam. The steam rises and turns a propeller that then generates electricity. So you can turn it into electricity. If you put those steps, if you're converting the energy into the right forms, you can eventually turn it into electricity that you could then use for all the things we do with electricity. Related to biomass is fossil fuels. So fossil fuels are just essentially old biomass. So when we talk about biomass energy, we're usually talking about energy from biomass that has grown very recently. So the ethanol that you might pump into your car at the gas station comes from corn that was grown, a year ago or so. Whereas with fossil fuels, we've got coal, oil, and natural gas that were biomass millions and millions of years ago, got buried under the earth. We have now excavated them to burn them. So it's essentially the same principle. It's just working with biomass that has been stored underground for a very, very long time instead of taking it directly off the plants. And our fossil fuels that we're using in our society today were largely formed during the Carboniferous and Permian periods. So this is about 350 to 250 million years ago. So it's a very long time ago. The processes that create fossil fuels continue to happen, but at such a much tinier scale and such a long time frame that we're essentially just, practically speaking, dependent on the stock of fossil fuels that was laid up during the Carboniferous and Permian periods. And to give you a sense of scale, when I talk about these periods 350 to 250 million years ago, after the Permian period comes the Triassic, which is the beginning of the age of dinosaurs. So the Triassic, Jurassic, Cretaceous make up the Mesozoic, which is when the dinosaurs were. So we're talking about stuff that was buried underground before there were dinosaurs. But there's a whole lot of it down there with a whole lot of chemical potential energy that was stored in it by those photosynthesizing plants in very, very ancient times that was just been sitting there until humans came along, dug it out. We can now burn it. That converts it into thermal energy. We use that thermal energy either directly, like to heat our house, or indirectly if we, say, use it to run an engine that generates electricity. Another common source of energy for human uses is nuclear. And when we talk about nuclear energy, we're generally talking about nuclear fission. So there's two ways you can get nuclear energy. We have nuclear fusion, where you take tiny atoms and you smush them together, and we've got nuclear fission, where you take big atoms and you break them apart. And so nuclear power plants that might be providing electricity to your house, depending on where you live, are working by nuclear fission. We have uranium atoms, we break them apart, that releases nuclear energy. That gets turned into thermal energy, which is used to turn a turbine, which generates electricity. So again, we convert it from one type of energy to another until we get the kind that we want, that electricity that's then easy to distribute to everyone's house, and then you can plug in your lamp or your TV or whatever it is you're doing. So nuclear power that's generating electricity for us here on Earth is nuclear fission, breaking up big atoms. But there's also nuclear fusion. And in fact, most of our sources of energy ultimately depend on nuclear fusion because that's what's happening in the sun. The sun's energy comes from nuclear fusion. It's smashing hydrogen atoms together to form helium atoms, and when it does that, it releases some nuclear energy that then becomes electromagnetic radiation and gets beamed out to us here on Earth and everywhere else in the solar system. And so there's a long-standing dream, if we could produce nuclear fusion here on Earth, that would produce enormous amounts of energy, and it would produce it relatively harmlessly. There are a lot of potential risks and waste products associated with nuclear fusion energy. It's often very controversial, but nuclear fusion would be much more convenient. The problem is that to sustain nuclear fusion, you need enormously high temperatures, which are just not practical for us to create on any sort of scale here on the surface of the Earth. That's why it can happen in the sun, which is, enormously hot, but we can't easily make it happen here on Earth. And so every few years, someone will come out claiming to have discovered the secret of cold fusion, which basically means nuclear fusion that we can make happen at a low enough temperature that it's practical to do it in a power plant on the Earth. And so far, none of those have panned out, but who knows? Maybe someone will figure it out, and that will produce another useful source of nuclear energy if we can do fusion right here on Earth. But for the time being, we're using either nuclear fission in a nuclear plant on Earth, or we're using the sun's nuclear fusion that we are then getting through several stages of transformation from there. Another common energy source for our society today is wind. And so wind is a product of convection. So if you remember back to our discussion of how thermal energy moves, that when we have a fluid, we get convection going, and that convection moves things from one spot to another, moves warm stuff to the cold areas and cycles the cold stuff into the warm areas to get warmed up, etc. Well, we have convection happening on the surface of the Earth because we are unevenly heated by the sun. Some areas lie directly in below the sun's direct rays and get heated up very warm. Other areas are away from direct sunlight and are not getting as much solar energy, so we get this uneven heating. But then our planet is surrounded by an envelope of fluid, our atmosphere, and so that atmosphere will move to try to even that out. So the uneven heating of the Earth creates movement in our atmosphere, creates this wind, and so then we can stick something into that wind to capture that energy. We can have the kinetic energy of that moving wind turn a windmill, and then that can produce energy in a form that we can use. And there's a lot of different ways that we can harness wind energy. Sometimes we can harness it very directly. If we have a ship with a sail on it, what's that doing is essentially just taking the kinetic energy of the wind's movement and converting that partially into kinetic energy of your boat, dragging the boat along with the sail. There have actually been proposals recently to develop sails for international shipping, because even though we think of sails as being like, oh, that's an old-timey technology, in the modern day we're thinking that might actually be a useful technology. It's could be very low cost way to harness wind power very easily to move ships. So you might see sailing ships coming back in our lifetimes. We can also, as I said, use that wind to turn a windmill. And so in the olden days, windmills would then directly do mechanical work. So a windmill would often turn a grindstone to grind grain into flour, for example. Or it would turn a pump. So that's why you have all those windmills in the Netherlands. They are turning pumps that keep the seawater from reflooding all of the low-lying areas in that country. But we also could see in a case like in the picture there, those are electrical windmills. They're turning a turbine that spins a magnet and creates a electric current. So they're converting the kinetic energy of the wind into electrical energy that then goes out to the grid and you can plug your stuff in. We also have solar energy. So I keep referencing the sun. And so a lot of our energy sources come indirectly from the sun, but what if we could tap the sun directly? So we've got this nuclear fusion in the sun generating electromagnetic radiation that's beaming out to the Earth, and we can do things with it. So one thing we can do is we can convert it into thermal energy. So the solar radiation can heat stuff up for us. And so that's the principle behind something like a solar cooker. So you may have seen these. It's basically a mirrored chamber. And if you put your food in the middle of it and point it towards the sun, the mirrors will direct the sun's rays right onto your food and will cook your food. So we could very directly use that solar energy. More common these days is what we call solar photovoltaic energy. So solar photovoltaic, or solar PV, is a system by which the solar radiation hits a special type of cell that then directly converts that into electrical energy. So it creates an electrical current when the solar energy hits those solar cells. So that cuts out a lot of those intermediate steps that you might get if you were, for example, if you had your solar energy that was being photosynthesized by a plant and then you were burning the biomass and using that to turn a turbine to generate electricity. You can cut out a lot of those middle steps by just directly converting solar radiation into electrical energy through a solar cell. We also have hydropower. So hydropower is another one that is actually ultimately driven by the sun again. Because another thing that solar radiation does when it hits the Earth is it causes evaporation. So the energy from the sun heats up the water and causes some of that water to turn into water vapor, which then goes up into the atmosphere and eventually comes back down as precipitation. Once that water has fallen back down to the surface, it then runs along the surface downhill until it reaches a body of water and eventually gets evaporated again. So the solar energy is driving that cycle of evaporation, precipitation, and runoff of water on the Earth. And so that solar energy essentially gets turned into gravitational potential energy when it moves that water up to the tops of the mountains. So when that evaporated water rises and ends up on top of the mountains, it now has a whole bunch of gravitational potential energy because it's now farther away from the center of the Earth. And then that potential energy turns into kinetic energy when that water then flows downhill. And then we can stick a turbine in that flow of water and convert that kinetic energy of the water flowing downhill into other forms of energy, such as electricity or just mechanical work if you have like an old-time water wheel. So we're again relying ultimately on the input of energy from the sun to run our water cycle, which we can then tap into for energy. And hydropower, we mostly think of that as being generated by dams that we place on existing rivers. So we've got a flow of water going down and we put a dam there so that we can regulate how that water passes through our turbine to generate electricity. But another interesting application of the basic principle behind hydropower is something called pumped hydro storage. So this is an attempt to address a problem with some types of energy, which is that they're not always producing energy when we need energy. If you have solar energy, for example, you can generate a lot of electricity from your solar panels during the day when the sun is shining, but they're generating no electricity at night, but you may still want to use some electricity at night. So you need to store that energy somehow. You need to store it up when it's being generated so that you have some to use when it's not. And there are various ways you can do that, right? So you could have a battery that you charge up during the day and then run down during the night. But another interesting way to store that energy is that you build two basins, so two ponds or lakes, one at a higher elevation and one at a lower elevation. Then during the day, when you're generating a lot of extra energy, you use some of that energy to pump the water uphill. So you are essentially giving it more gravitational potential energy because you're putting it up on top of the hill. Your pump that's driven by your daytime solar panels. Then at night, when you need that energy, you release it to run back downhill. So now that gravitational potential energy turns back into kinetic energy, and it turns your turbine as it runs back down into your lower pond. So you can essentially store energy by pumping water uphill and then get that energy back out by releasing the water downhill. So that is what's called pumped hydro storage. And it's a thing that is under consideration in a lot of parts of the world where they've installed a lot of energy sources that raise those questions about how do we store this energy for when we're going to need it because we're not generating it continuously. Another form of energy that you may encounter is geothermal. So with geothermal, we are tapping thermal energy that exists down inside the Earth. So in a future lesson, we'll talk more about the interior structure of the Earth. Key thing to know here is way down inside of the Earth, it's quite hot. And it's quite hot due to radioactive decay in the core of the Earth. So this is another one that has nuclear energy way down at the base of it. That radioactive decay keeps the interior of the Earth warm. And so if you drill a deep enough well, you can tap into that thermal energy that is down there inside the Earth. And you can either use it directly. You could just bring that heat up, right? Pump some water down there to heat up and pump it back out, and then just use that for heating directly. Or you could use it indirectly. You know, once you have that thermal energy, you could use that to turn a turbine, generate electricity with it. And that is the main energy source for the country of Iceland. Iceland happens to have very easy access to hot underground temperatures. So the heat inside the Earth is very close to the surface in Iceland. That's where this photo is from. And so it's very easy for them in Iceland to tap into that geothermal energy. But the technology is advancing to the point where you can access geothermal energy practically anywhere in the world. So I have some friends who live pretty close to Pittsburgh, and they recently got a geothermal system installed at their house. And so there's enough heat down under the ground just around Pittsburgh that they're able to make use of it to heat and cool their house. I say heat and cool because you could also use a similar principle for cooling. If the surface is hotter than it is down below, you could essentially do the thing in reverse, that you could pump water down there, for example, and have it cool off, have it lose its thermal energy to the cooler surrounding stuff, and then bring it back up to cool a building. And that's actually done with buildings in downtown Pittsburgh. There is cold water in an aquifer underneath the city, and they pump water from the buildings downtown down into that aquifer to cool off and bring it back up to cool those buildings during the summer. And then one more source of energy that has a lot of potential but is not very extensively developed is tidal energy. And so this one is interesting because it's one that doesn't ultimately go back to nuclear energy. All those other ones, if you trace them back enough steps, you get something nuclear. But with tidal, you actually don't, because tidal energy is the result of the moon's gravitational pull on the Earth. So as the moon orbits the Earth, it's pulling everything towards it, but it's going to get more grip on water because water can move. Water's more flexible, so that water is going to get pulled towards the moon more. And so that's going to raise the relative sea level wherever the moon is going by. So we get our cycle of tides, right? The water level rises and lowers in a cycle over the course of the day. So that rise and fall of the water that's created by the moon's gravity can be tapped into and converted to other forms of energy that people can use for other things. Now, the simplest way to use tidal energy is, you may have hear about ships waiting for the tide to go in or out to launch or dock. So there you're just using the rise and fall of the tide water to bring your ship into shore or carry it out away from shore. Much easier than trying to fight against the tide. That's been done for as long as we've had ships. But in modern times, we've found ways to essentially put some sort of energy generating turbine into the water so that the tides spin that and generate electricity. So this is the least developed of these, but it's one that potentially has a lot of energy to offer for particularly coastal areas if we can get the right technology that can efficiently convert the energy from the form that it's in to a form that we want to use it. Because that's the key thing, is there's a ton of tidal energy out there, a ton of energy involved in the Earth's tides, but it's not in a form that people can easily use it. We need to convert it into something like electricity that we find useful and concentrate it in the locations where we're going to make use of it. That's the challenge with developing energy sources, is converting it into a useful form and getting it to the people that want to use it. So I've talked about those different energy types, so I want to finish by just giving you a little glimpse at what that energy use looks like for the United States. So these are federal government statistics about different energy types. And on these graphs, they've classified them a little differently than I did in my presentation. They've, for example, broken out the different kinds of fossil fuels so that you can see the different trajectories of gas, oil, and coal. And then in the upper one, they group all of the renewables, which are the non-fossil ones together, and then, or non-fossil and nuclear together. And then the lower one is the renewables broken out. And so you can see overall big increases in the amount of energy being used in the United States over the course of the period that's being shown. And in particular, we have big increases in both renewables and 2 out of 3 of our fossil fuels. So coal use in the United States peaked in 2008 and has been declining ever since, but natural gas and oil continue to rise, as do all of our different types of renewables, aside from hydropower, which is kind of flat. We're not building any big new dams, so we're not bringing more hydropower into the system. You can see it's been kind of level since the 70s, but things like biofuels, wind, and solar have gone way up over the last couple decades. But at the same time, fossil fuels also going up. Our society is just using a lot of energy these days. So that is it for this lecture, and I will see you next time.